Okay, so now we're going to continue looking at bending moment diagrams. So last video we covered shear force, and this is the examples from that. So we're just going to build on this now, and we're going to do our bending moment diagrams. So we'll start, as always, with something nice and simple. So again, we need an axis, and that follows on down underneath our initial diagram up here, so that everything lines up. So we need some sort of horizontal scale, and obviously this is an axis, so it's a graph. So we definitely need a vertical scale as we plot our values. Okay, so a bending moment diagram is a little bit more complicated than the shear force diagram. And what we do for the bending moment diagram is we take the moments about each force. Yeah, so we'll take a moment about there, we'll take a moment about there, we'll take a moment about there, and then we plot those values on our axis and we join the dots. So let's just work our way through that. Okay, so I'm going to move this little red dot to show where we're taking moments about. So I'm just going to take moments about reaction force 1. Okay, and we said that was 10 newtons. And as we know, a reaction is a force times a distance. So the distance from reaction force 1 to the red dot is 0, so it drops out of the equation. So we only have to worry about two things. Now, because our beam is in equilibrium, we can take moments at any point in any direction, and we should get the same answer. So we'll check that's correct, perhaps on this example over here, because there's a bit more to this one. But for the moment, take my word for it. So here we could either take moments to the left, or we could take moments to the right of the point we're taking moments about, and we should get the same answer. So if we take moments to the left, well, what is there to the left? There's nothing to the left. So the answer must be 0. So let's start there. Let's copy our little dot, and we'll move that in line there, and that's a big fat 0 there. Okay. I think I need a construction line, don't I, just to make sure we can get that. Oopsie daisy. No. Sorry, bear with me. Right. So we place a point on our graph line at 0, or on the vertical axis at 0, 0. Took more placing than you'd imagine. Okay. So now we move on to our next point of interest, which is just there. So we take moments about this point. Now here we can either go to the left or to the right, and it makes no difference because there's the same number of forces and in fact the same value of a force. But what we need to remember is that it's a force times by a distance. So we actually need to put some distances on this, don't we? So shall we do that now? Let's do that now. Let's say if the entire thing is 2 meters, 2 meters. Yeah. Let's just write a value there, CV. So 2 meters. Oops. Okay, so the entire thing is 2 meters long. So that means it's going to be from our point to the end is 1 meter. Or indeed from our point to the end the other way is 1 meter. It's going to be the same calculation, isn't it? Okay. So when we're doing bending moment diagrams, we count downward forces as negative and upward forces as positive. Okay, so we've got to bear that in mind. When we do bending moment calculations, downward forces are negative, upward forces are positive. Okay, and that's because we count as positive or negative bending moment by the way that the beam bends. So if we look at these two smiley faces I prepared earlier, a sag like that, so I've called it a happy sag, because we put a little smiley face there. A sag is negative, and a hog, where the beam bends upwards, is a positive. And I've called that a sad face. So, you know, hopefully that might help you to remember. Yeah, so probably just should put some text in there, shouldn't we? Positive. Yeah. Happy sags. Yes. So positive, and am I contradicting myself here? I don't think I am. Okay. That's negative. Okay. Is that right? Have I got that the wrong way around? A downward force would be a happy sag, wouldn't it? It would make something sag. Yes. So that's got to be correct. I'm going to double check that after I finish this. I do hope I've not got it wrong, because I'm halfway through the video. I don't want to have to start again. Right. Okay. In fact, I'm going to pause and check now. Yes, no, I thought that was wrong. There we go. It's the other way around. Positive if it's happy. Of course it's positive if it's happy. Why wouldn't it be positive if you're happy? Yeah. If we imagine that the force was just pushing at the end, so the force is pushing at the end, then it's going up from its fixed position, isn't it? And that's a positive happy sag. Okay. Of course it's positive. Yes. Good. I'm glad I've got that sorted. Didn't think that was right. Good. So it's a positive. A happy sag is positive because we're pushing upwards, and a sad hog is negative. Of course it is. Sad, negative. Yes. Stop being so negative. Because we're pushing down at the end. Okay. All right. Good. Glad we've got that sorted. Good. Happy days. Positive days. Good. So now we're taking moments about this point here, this little red dot, once more. And what we're saying then, so our moment would be 1 meter, because it's 1 meter to either force, because it's in the middle. So it's our force times distance. So it's going to be 10 times by 1 meter. Okay, and I don't think I need to lay out a calculation when I say that 1 times 10 is in fact 10. Do I? I'd hope I didn't anyway. Okay, so 1 times 10 is 10. So we put a dot halfway along at 10. So I'm just going to extend this construction line to there. And I'm going to count at 1, 2, I'm going to copy this, Control CV, and then I'm going to put that 5 up. So 1, 2, 3, 4, 5. Okay, so let me make sure I get that in the right place. Okay, so there's our dot in the right place at 5 up. So obviously we're doing 2 squares to 1 square to 2 newtons here. And then finally we come to our last point of interest. So let's move our pointer along, and that's reaction force 2. And obviously the reaction force 2, we can go to the left, in which case we'd have to do 1 calculation, or we can go to the right where there's absolutely nothing. And so that must be, once again, a 0. So we'll just put that in the correct position again. So you can see here we've marked, oops daisy, let's remove that. We've marked on our graph a 0 point, and that's in line with reaction force 2. And all that we do from there is, I'll just take my construction thing there, is we very carefully, we just join up our dots. And that is our bending moment diagram. Okay, so that's a very simple bending moment diagram just there. Oops, daisy. Very simple bending moment diagram. But that's essentially how we do a bending moment diagram. So we'll have a look at this. That's not what we want to do. We'll have a look at this example here, and we'll just go through that to create a bending moment diagram, and then we'll unpick a UDL example. Okay, right. So I think I need to move this lot out of the way, don't I? Yes, I do. Oh, that's annoying. Right. So let's put that there. Oh, that fits nicely there, doesn't it? Right there. Excellent. Okay, so let's set up another example. I'm going to move down a little bit, give myself some more space, because that comes down quite a way, doesn't it? Right, so once again then, there's going to be some scrolling involved this time. Let's start with our first force. So we can take moments about that force, and we can go to the left or to the right. Well, to the left is 0. That's a much easier calculation to do. Let's go that way. Okay, so let's mark a 0 on our bending moment diagram. Okay, there's a 0 point marked on our bending moment diagram. So we're going to move to the next point of interest, which is our 14 kilonewton force, and we're taking moments about our 14 kilonewton force. So again, we can go to the left or to the right. If we go to the left, we have one force to contend with, and if we go to the right, we have two forces to contend with. So let's go to the left because that's easier. Let's not make life difficult for ourselves. So what are we saying? We are saying we have a positive upward force, which is 18.75, and that is 2 meters away from the point we're taking moments about. Okay, so 18.75 times by 2 meters will give us our moment. So let's put that in. Okay, so 2 times 18.75 gives us 37.5 kilonewtons. So I've just gone up 4 squares because I can't do partial squares on here. So we're going to be roughly to scale, but not as accurate as perhaps we could be. So 37.5 is that dot there, and that's in line with the point that we've just taken moments about. Okay, so let's move across then to our next point that we're taking moments about. And again, we can go to the left or we can go to the right. Don't worry, I've not forgotten that I'm going to show you that we get the same answer going left or right. But let's just work our way through a bending moment example first. So let's go to the right because there's only one force to the right, whereas there's 2 forces to the left. Okay, so we're going to the right. So the distance between this force and this force is, well, 8 minus 5, so that's 3 meters. Okay, so we've got 3 meters and we've got 17.25. So we just multiply 17.25 by our 3 meters and then we place that point on our graph. And that gives us 51.75 kilonewtons, no, 51.75. And so we've placed that in line with the point that we've taken our moments about. So I've just counted up 5 squares there because I can't do 1.75, so I'm just rounding to the closest thing. Okay, and then finally we move on to our final point of interest, which is our final force here. And of course we can go to the left, in which case we'd have to do 3 calculations, or we can go to the right. Well, there's nothing to the right, so our answer must be 0. So we come back to our final thing, and that gives us back to a 0 there. Okay, and then all we do then is we just join up our dots in the finest tradition of making a graph. I mean, I can suggest that when you do this, you don't do it the way I've done it, but you do your calculations first, and then you can pick a suitable scale, because sometimes your numbers might be quite large, and your first number's quite small, and then you have to go up to 120 or something on your second number. You're like, I've not got enough paper. So if you do your calculations first, then you can select a suitable scale afterwards. Okay, and that's it. That's our bending moment diagram. Let's just move that there for a bit of tidiness. And that's our bending moment diagram. That's how we do a bending moment diagram. Right, I said I'd show you that it didn't matter whether we went to the left or to the right. We should get the same answer because, it's all in equilibrium. And, what we're saying is, clockwise moments and anti-clockwise moments must equal each other for equilibrium. So going to the left or to the right, we should get exactly the same answer because we're in equilibrium. So let's just unpack that a bit. So we're going to go through this one. So let's bring that back. Let's go to the left first. Going to the left, we have our first point of interest is this 14 kilonewtons, and that is 3 meters from there to there. Yes, it's 3 meters away from the point we're taking moments about. So that's going to be 3 times by 14. So we'll just set this up as a calculation. So I've just copied this and pasted it down. Just copied this and pasted it down here just for a bit of clarity. So we're just showing that we can take moments to the left or to the right and we'll get the same answer. So to the left then, we've got a downwards force, and we've got to remember that if it's a downwards force, that's a minus number, okay, and that's times by a distance of 3, yeah, 5 minus 2 is 3, so from here to here is 3 meters, okay, and then we add that, we've got 18.75, which is our reaction force there, and that's 5 meters away from the point we're taking moments about. Okay, so if we just quickly plug those numbers into our calculator, or you can do it in your head if you so desire, and let's see what we get. And that gives us an answer of 51.75. Oopsie daisy. Let's try that again. Numlock. 50. Yeah, no. Numlock. 51.75. There we go. Kilonewtons, always. Yeah. And as some of you might already be observing, that's exactly the same number that we have there. And that was the answer that we... Oh, I didn't copy and paste it. I just copied it. I didn't... Oh, that's annoying. Right, hold on just a second. Right, let's try that again. And as you can see, that's exactly the same answer we got when we went that way. And we said 17.25 multiplied by the 3 meters from here to here. But for the sake of completeness, let's just double check that. So that was going to the left, and so now we'll try to the right, and we'll just put that in a sum so we can just double triple check that we're absolutely correct. And as we can see, that would be 17.25. That's that force there. We're going to the right, remember. 17.25 multiplied by 3 meters, which is 51.75. So hopefully that's shown that it doesn't matter whether we go to the left about the point we're taking moments about, or to the right, we end up with the same answer. Okay, so the final thing that we need to do about bending moments is we need to look at what happens with a UDL. And with a UDL, it's a little bit more complicated, unfortunately. So here's our UDL example. We'll set that up. Okay, so starting with this example, again, we can go to the left or we can go to the right. Oops, daisy. We can go to the left or we can go to the right. So there we are, let's demonstrate that. We can go to the left or we can go to the right. Now obviously if we go to the right, we've got two things to think about. If we go to the left, there's nothing there, so the answer must be 0. So you can see I've already put a dot in the correct place there. Okay, now the maximum bending moment for a UDL will be at the center position. But what we get when we do a UDL on a bending moment is we get a curve. Okay, we get a parabolic curve over the UDL. So we might need more than one point, and I go through that in a presentation a little later on. But we might need more than one point. But essentially, we use the 35 newtons that we've got for our total force. That seems to have vanished somewhere in the copying of things. So let's just put that in there. Don't know where that's vanished to. Okay, so we've got our 35 newtons. So we take moments about that point. So there we go. And that becomes the maximum of the curve. That's where the curve would turn, would be the center point of the UDL. So if we're taking moments about this point, then that's going to be 5.5 meters to the reaction force. Is that right? Yes, 3.5. 5.5 meters to go mad, to the reaction force from our little red dot. Obviously, it doesn't matter whether we go left or right because it's the same calculation. It's an upward force, so it's positive. Yes, which I probably should have. Did I clarify that? Yeah, 14 there, minus 14 because that's the downwards force. Okay, and so 17.5 multiplied by 5.5 gives us 96.25. Okay, and so that becomes the maximum point of our curve. So if you'll just bear with me, I'll attempt to put a nice curve on things and I'll be back. So that essentially becomes our bending moment diagram for the UDL, because if we took a moment about our corners, the end or the start of the UDL, if we took a moment about, well, let's move our point so we can see. If we took a moment about here, then no, I'll shut up, hold on. Right, let's just scrub those last few seconds. So now the only question that remains is, where does this curve start and stop? So we need to take a moment about the end of our UDL so we can define that. So if we take a moment about that point, then we're going this way. We encounter our upward force there. Okay, so from the end of our UDL to our upward force is 2 meters. So 2 multiplied by our force of 17.5 is 35. And so...
I didn't quite catch that. Try repeating your calculation.
Thank you for that. So 17.5 times by 2 is 35. So we start and stop our UDL, he says, at 35. So let's move that up to, let's put that up to 3 on here, because obviously I can't do half measures here. Yeah, so let's put that up to 3, and then we can place that at the end there, and we can do one more at the other end, and then finally, whoopsie daisy, let's not do that. Finally, we're back down to 0 at this line here. So let me just get that in place, and then as before we join up the dots. Okay, so let's just do that and join up our dots. Is that there? That's there. Excellent. Scroll down a smidge, join up our dots, and let's get one more line in, and we join up our dots. So it might be that to do our curve accurately, especially if we're doing it by hand, or even if we're doing it with a couple of twiddly bits like that, to get a more accurate curve, we actually take our UDL, at various points along our bending moment at various points along our UDL. Yeah, and then let's say at each point we could go to the left or the right. Yeah, so we could go to the left there, and then we'd have to put the point load. So from there, let's say that's 1 meter into our UDL, for argument's sake. If we're 1 meter into our UDL, then we have to say, well, that's 1 times by 5 newtons. So the 5 newtons goes at half a meter away from the point we're taking moments about. And then we can do the calculation. So we'd have a down force of 5 newtons there at the halfway point. Yeah, we'd have a down force of 5 newtons there at the halfway point. That's not the halfway point, but I can't do the halfway point. And then we'd have an upwards force of 17.5 at 3 meters, because it's 3 meters from there to there, and we can do that at various points. Okay. Like I said, I do go through that in more detail in one of the presentations on the resources. All right, so that's how we deal with UDLs on bending moment. We'll go into this. We'll do lots of practice on this to get us head around it. But hopefully that's enough to get us started. All right, thank you very much.